Okay, so we are going to do something called the goodness of fit test, and this test and the test that we will do, they're all related, and they're all meant for one type of data, which is called qualitative data. Or categorical data. But this one test can be used for discrete data also, but I won't get into it. Your book talks about tests for qualitative data in chapter 12. I'll just leave it be. What is qualitative data? Statistics 2023. The root word for qualitative is quality. Do we agree? So what we are going to assess is some sort of quality, and I'll start with a very lame example, hair color. I know what's going to come next. With 95% confidence.
Emotions?
Emotion, okay, usually that's not the next one, but it's eye color, right? When I say hair color, students usually say eye color. What else? So emotions, anger, happiness, sad, existential dread, all of those. What else? Want an example that I can relate to here. So what we have here is a distribution, and we have 4 different categories, which is why we call it qualitative data. And what is the variable? It is the type of telecom, and we are going to look at cable, Netflix, Prime, and Hulu. And it is claimed that it is equally likely among the 4 levels or categories that we considered. We want to perform a test to determine if that is true or not. Here's the question. Even before we start, do you believe that it is equally likely? No. So at the end of the day, we are going to reject the no. Okay, we'll see. Now, there are assumptions in terms of what the frequency should look like for a goodness of fit test. Those assumptions are summarized in your textbook. It's very few assumptions. Make sure you read them prior to starting the homework, because it might actually say in the problem, okay, what is the assumption for this particular test, and you have to answer. One of the most commonly used assumptions is that each of these count should be greater than 5, which it is not in this case, but for the sake of it, I'm just going to go with it. Does that make sense? Okay. As always, step 1, we define the null and the alternative. Here, we're simply going to state that the null is that the probabilities are the same for all 6 levels or 4 levels. So P1 equals P2 equals P3 equals P4. What are 1, 2, 3, and 4? 1 is cable. So we've got 4 levels, and my claim is that they are equally likely. What would that mean? What are the chances of each of them? 25% each, or we can simply say it is 1/4. In words, what would this mean? It simply means that the type of telecom is equally likely among FGC students. The alternative is simply the opposite of what we have. We're going to say it is not equally likely. And even before we start the problem, we sort of have an idea that we are going to reject the null. We will see. The amount of type 1 error that I'd like to set is 5%. In other words, the probability of error in rejecting the null under the null that I have assumed, which is P1 is equal to P2 equal to P3 equal to P4 equals 1/4, is 5%. For us to reject, it has to be 5% or less. Okay.
So going back to the null and alternative, so in the example, it says that the claim is that they are equally likely to occur, but they were swapped over here, and I just wanted to double check.
Swapped how? Okay.
Well, if it was, if the claim was to be equally likely among the four of them, wouldn't that be our alternative?
Well, I see why you're getting confused there. So typically, we have the alternative to be the claim, right? Now, in a test like this, that doesn't apply. So what we would always test for is that they're all the same and they're not the same. We need to have the null to have the equality. So if we say that they're all equally likely, then it should be the null. So if I find evidence toward the alternative, I'm simply going to say that the claim cannot be true. And I'll bring in the goodness of fit part later on, and I'll finish another table. So what we observed here would be the observed frequency. So we have 0, 14, 1, and 3. And based on the observations that we have, the sample size N is 18.
Oh, you switched Hulu and Prime.
Oh, crap. Wonderful. Thank you. In order to find the test statistic, we have to find something called the expected frequency, which is E. Why do we call it the expected frequency? We call it the expected frequency because under the norm, if that were to be that is the norm, so if I have to conclude that they're all the same, in the sense that the proportions or the probabilities are the same, then I need to expect to see what are the expected frequencies that we're going to compute. How do we compute that? So we know the sample size, and we can't find a count for each of those cases. So 1/4 of 18 What is 1/4 of 18? Oh, sorry.
4.5.
It's not B. It's just the counts in each case. Since I want it to be 1/4 for all of those 4 cases, I need to have 4.5 across, right? The same frequency. So 4.5, 4.5, 4.5, 4.5. And you may say, well, why do we want a test? But in this particular problem, we technically don't need a test. Seems quite obvious. But we always go for a statistical test because if you look at Netflix, it is quite clear cut, right? If you look at Hulu, it's very close to each other. So you've got to account for the variabilities that go up and down. So those are the expected frequencies. Do we understand expected frequencies? Okay. As always, the test statistic in this case has a chi-square distribution with degrees of freedom equal to k minus 1. And you may say, well, what is k? K is simply the number of levels that we observed. So how many levels do we have? 4. So the degrees of freedom would be 4 minus 1, we have 3. I'll just write some words. So the test statistic would be the sum of all O minus E squared divided by E. So the test statistic chi-squared, I'm going to sum all O minus E squared divided by E. For the first level, what was the observed frequency? 0. What do we expect? It is 4.5 squared divided by E, 4.5. For the second level, it is 14 minus 4.5 squared, O minus E divided by E, which is 4.5. Third level, which happens to be the total or prime, in prime, 1 minus 4.5 squared divided by E, for the case, is 4.5. And the last level for prime, the Hulu, it was 3 minus 4.5 squared over 4.5. Yes? Okay, so if we end up having a large sample, even a linear distribution, we don't want to sit around and do this, right? Take a lot of time. So what we're going to do is we're going to enter all the observed frequencies in the first list, so which is 0, 14, 1, and 3. All the expected frequencies in the second list, 4.5, 4.5, 4.5, 4.5. So L1, L2, L1 is observed, L2 is expected. Second node to exit. So L1 is observed, L2 is expected. So what I'm going to do is type second 1, L1, minus second 2, L2, squared, O minus E squared, divided by E. E is in L2. So I have L1 minus L2 squared divided by L2. We want to store these values to another list before we can find the sum. So right above the on button is the STO button. STO stands for store. I'm going to store it to list 3, so second 3.
Could you just go to the header and list 300 there? Would that also work?
Yes, you can.
Thanks.
Good.
Can you say that one more time?
So we want to first find each of those O minus E squared divided by E, but we have to store it to the third list because we want to find the sum of everything. So to do that, we need another list. Does that make sense?
How was it that you did it?
Oh, about the store place. On, right above on, you have STO. So when we click STO, it should say that. And those are the values that we have. So second mode to exit. And press start. Go to calc. Option 1. One variable statistics of the data in list 3. Because we found O minus E squared divided by E, and we saved that information to list 3. So second 3. Don't look at the first one, that is the mean, right? We don't want the mean. We simply want the sum of O minus E squared divided by E, which is given by the second row, 27.77. Good. The first row is X bar, which is the average of all the values in list 3. We don't want the average, we want the sum. So look at the second row, the value is 27.77. Good.
I'm getting wild numbers here, I'm not sure what it all. For my X bar, I have 232, and for, I only have 122.
Okay.
14, 1, 2. If I go to L3, it says 0, 82, 4.5, and 40.5.
Would you make sure on one of those that you use L3?
I believe so.
So you need to get 4.5, 20.056, 2.72, and 0.5.
Okay, so I'm gonna clear list 3, and I'm gonna try to do that again.
Are you trying to just do it in the header?
No, I did it on the main screen. I
Okay.
did L1 minus L2, close parentheses and square, correct? And then divide by L2,
Yes.
and then store to L3.
Yes.
I thought that's what I did, but I must have did something wrong before. It's working now.
Okay. So we get 27.77, and that is the value of our test statistic. Good. What do we use to find the conclusion? We have two methods. We could either use the critical value method or the p-value method. From a long, long time ago, do we know what a chi-square distribution looks like? I kind of gave you a pencil, don't you? Does it look like a bell-shaped curve? A chi-square distribution is a right-tailed distribution in the sense you cannot have a negative value with a chi-square. Well, if you look at that, the numerator is always positive, yes? The denominator is a frequency. Could a count of the number of things be negative? If you're counting the number of people in the classroom, the number of apples in the basket, number of this, and number of that, could it be negative? No. So all of those values are positive. The area and the right tail is alpha, and alpha is 0.05. Another important thing to note here is a chi-square test, a chi-square goodness of fit test is always right-tailed. One less thing to worry about. So if we find this critical value, we can determine whether to reject or not reject null. So that critical value is denoted by, I'll write here so you can see. One minus alpha, comma the degrees of freedom. So in this case, alpha is 0.25. So 1 minus 0.25 is 0.95. What is the area in the bright tail? In our problem. 0.05. Keep in mind, if I had to use a calculator, then we would always look at the area below. But for the table, we are looking at the area above. What is the area above the critical value? It is 0.05. So go all the way to 0.05. And what is the degrees of freedom? It is k minus 1. 4 minus 1, we get 3. So 7.815. Good? Yes? Does the test statistic, which is 27.77, fall in the rejection region? Yes. The critical value is 7.85, and the test statistic is way that way. Probably somewhere over there. Should we reject a null? Yes. So the conclusion here is that we reject the null because the test statistic falls in the rejection region. And what is our conclusion? If we reject the null, then are we saying that the type of telecom that HSU students watch is equally distributed or not equally distributed? They're not equally distributed. So is the claim true or false? The claim is that they're all equally distributed, and the test says, well, doesn't seem that way, so it's the claim or true or false? The claim is false. So in a test like this, the claim statement could either be the null or the alternative, and which is why we've got to be careful in interpreting the null and the alternative properly. Did you have a question?
Would you mind just pulling up the screen, because I can't really see much of it from this.
Oh, this one?
Yeah.
Can you see that?
Yeah.
Because I have to pull that down. So the p-value is simply the area above the test statistic, and the test statistic here is 27.77. By area, we mean the area under the curve. So past this point, how much area do you see under the curve? A large area or a small area? Extremely small. Yeah, okay. It's an extremely small area. So in your calculator, the function is chi-squared CDF. So go to our usual spot where we find TCDF, normal CDF, and circles. The lower bound is the test statistic, 27.77. The upper bound is infinity, E99. What goes next? Degrees of freedom, and what is the degrees of freedom in this case? It is 3. And what do we get?
I got 4.06.
We're missing something.
Has the E -6?
It's a probability, it cannot be bigger than 1. So it is 4.06 times 10 raised -6. So it's approximately 4 in a million chance. So under the null, and based on the current data, if I rejected the null, the chances that I could be wrong is 0%. So could I comfortably reject the null? Yes, because the probability of me being wrong based on the data and the current null is close to 0%. So we can easily say that we reject the null. Does that make sense? Okay. All of this can be done using your calculator. So we have L1 and L2 saved already. Let's exit out of that bit. Press out, go over to tests, and scroll down. Don't pick chi-squared test, that's for something else, and I'll get into that later. I should say chi-squared GOF test, which stands for chi-squared goodness of fit test. And it is asking you for the observed frequencies and the expected frequencies And I'm saying that the observed frequencies are in list 1, the expected frequencies are in list 2. The degrees of freedom is n minus 1, or k minus 1, 4 minus 1. And what do we see? What is the test statistic? 27.77. The p-value is 4.04, 3 times 10 raised negative 6. The degrees of freedom is 3. And then there's this fourth line that says CNTRB. Can you guess as to what that means?
Isn't that L3?
Very good, that's L3. But what would CNTRB mean? Take a guess. It's a word.
Central.
Okay, good try, Samantha. It's contribution. So, why is that important? Of all the values that made this test statistic bigger, so the test statistic became 27.77. Which is the most significant player? In this case, I traced it, but it was the second level, 20.0555. And what level did it correspond to? Of 4 times, 4 different methods of communication, which one was it? 20.055. It was Netflix. So the significant contributor in finding or in concluding that they're not the same is Netflix. Netflix is the one that strayed far away from what we expected. Does that make sense? No. You may say, well, I could have come to that conclusion just by looking at the raw counts and saying Netflix is the one that strayed far away from the expected frequency. And the reason for that, we can't do that. The reason for that is what if I had 24 there, 14, 32, 9. You know, there is variation, but things are very close to each other. Then I can't say which one is contributing the most. So we can't base it on the raw counts, rather we have to base it on the statistic that we computed, which is the chi-squared statistic. So each value in list 3 is part of the chi-squared statistic. And which one is giving us the most contribution? It is the case that corresponds to Netflix. Does that make sense? Yes.
So goodness of fit is just measuring which one contributes the most.
Good question. It's about to get there. So even though we can identify which one is contributing the most and rejecting the norm, the purpose of goodness of fit is to determine if whatever claim that we have fits well with what we observed. That's why we call it goodness of fit. If you can't see that clearly, can I erase here? Yes?